Hi, Internet. This is Sean McBride and Kait Moreno.
Hey,
And
everyone.
today we're going to be talking about Chapter 4 of the Rust programming language book. How are you doing, Kait?
I'm doing well. How are you?
Good. It's been a couple of weeks since we did one of these. What have you been up to lately?
Same old. Mostly, mostly work.
Mostly
Baking.
work.
Been baking some pies.
Ooh,
Yeah,
what type?
cherry. Got some.
Okay, that's
Yeah,
American classic.
it is. Yep. How about you?
Yeah. I mean, nothing too crazy except for my wife Erica had her identity stolen. So if you haven't like locked down your credit scores and stuff, maybe it might be something worth considering.
You mean freezing your credit, or is
Yeah,
that
yeah.
different?
So I had to create like an Experian and like a different account for each of the credit things and freezing it.
Yeah, I've never done that before.
I guess ownership, we need to own our identities and own our credit scores. And
It's
we're
true.
going to be talking about owning things on the heap. Yeah. So I don't know about you, but I found this chapter to be kind of a tough one.
Yeah, very conceptual. But after going through it a couple times, I feel like I have a much clearer understanding of how things are functioning under the hood. Like
Mhm.
being a JavaScript developer, those things are super abstracted. So this gave them some shape in a way for me.
Yeah. Yeah. It's like unpacking the black box and it's like, whoa, we have different parts in here. There's like a stack, there's a heap, and they do things.
Yeah. For me, the stack was pretty much just like the concept of last in, first out, but not
Hmm.
I didn't quite understand what that meant in the context of like managing memory.
Yeah. Stack's pretty neat. It's like kind of got some superpowers too, right?
It does, yeah. So maybe we should start there with the stack. So we're talking about the stack and the heap, and those things refer to parts of memory that your program will have access to when it's running. And these two structures, like they have different advantages depending on what your program needs. And so, like I said, the stack is a last in, first out data structure. So if you think about a stack of plates, the plate on the top has to be the first one you take off, or else you'll have a big mess. Adding data to the stack is called a push operation, and removing it is called a pop operation. And the big advantage of the stack is that it's really quick to access data from it, because you don't have to really search for anything. You know it's always going to be on top, the thing you want to access. And the second advantage is that everything on the stack has to have a known fixed size, so it can't grow or shrink. And those things make it really useful. But the downside to the stack is that you can't do a lot of dynamic stuff. Like you can't have data that grows or shrinks. And that's what we have the heap for.
I guess that resizing thing is kind of something you really take for granted in like a scripting language.
It is.
So like I'm kind of a programming language nerd a little bit. Like I don't know if you saw, I did a blog post a couple of months ago on like COBOL. Like I would never take a COBOL job, but I just like seeing how people kind of did things like decades ago.
Mm-hmm.
And one of the crazy things about COBOL was you had to basically statically define all your variables. And
Mm-hmm.
then for like a string, you have to basically create like a 100 character buffer and then just kind of manipulate that as you go. Yeah, it's like if you are limited to like just having a particular data size, it's
Mm-hmm.
kind of a pain. So the heap gives us some pretty neat superpowers too, but it's a little bit more complicated.
Mm-hmm.
The stack, like what you're just talking about, Kait, like we like if we invoke a function, like I kind of think of like here, if main invokes add, we
Mm-hmm.
push this new scope on top of our call stack, and then we have our static variables in here. And so if we want to be able to have some dynamic memory, we have to use this area over here, the heap. This is kind of like a C programming language kind of centric example, but it's like here in the heap, we're just kind of like talking about these arbitrary addresses of memory. And so over in the heap, you don't have really a concept of like a variable name or anything like that. We just have like this byte is 2209260, and it's got this value. And if we want to be able to access that, like, I don't know about you. Can you remember this number?
I don't think so. I don't think it's going to happen.
Are you a savant? Maybe you could do it. Yeah, I definitely couldn't. So like for me, having like a human readable label is pretty important. And to be able to do that, we have to have some sort of variable, and that has to be associated with some sort of scope, like just everything else. So the way we have that happen is by having some sort of variable that keeps a reference to where in the heap is that thing stored.
Mm-hmm.
And so if like we say, I want ages, and ages is like, okay, check out the heap, go to this memory address. And then it's like, okay, go over here. And then it's like, there's our value. And so since we have to kind of do like, I guess a couple of hops there, I imagine that it's a little bit slower, maybe, do you think?
Right, because you have to, well, actually, I don't know if it's slower because you know exactly where you're going. So it's like you're accessing it by an index like you would from an
Mm-hmm.
array.
Oh, that's interesting. So like you look at these things and you kind of think of the heap as like a big array of data.
Kind of looks that way.
Yeah, I think I'd agree with that. That's pretty cool. I guess like all of computer memory is kind of like one big array then.
It might be. I think
One
we're onto something.
Huge 60, yeah. Whoa. Boom.
So you could say that ages variable is pointing to.
Oh yeah.
Something?
So like in C, this would be a pointer. So it would be like to be able to actually like get this address, you have to use this special API, and it's got some obscure things like malloc or free. Mm-hmm. And so you basically are like, hey heap, I need like 64 bytes or whatever. And malloc is like, all right, here's your address to your bytes. And it's
coming
like,
right up.
Thank you. Awesome. And then it's like, okay, I'm going to store that in a pointer so I can kind of keep a note of where that is. One of the things that's kind of a pain with C is this pointer. This is on the stack. So like mm-hmm. when the frame gets popped, it gets cleaned up and stuff. Mm-hmm. But the call stack doesn't really know anything about what this 2209260 thing is. And so this never gets actually cleaned up. And so that's kind of like, I guess, what like a garbage collector would do in JavaScript. That means that like at the end of a function, it's up to the individual developers to go, okay, here are all my pointers. I need to call free on each of them.
And people make mistakes. They're good
we
at
could
that.
Make this a really, we could make this a really, really long screencast if I was going to show some really terrible C code that I wrote at school this past semester.
What kind of mistakes did you run into?
So I definitely have a lot of memory leaks. And with memory leaks, it's like it runs, but it just kind of creeps up the memory utilization over time. Mm-hmm. And so it's kind of like, it's academic code. You're only going to run it for like 2 minutes, and then you're just going to quit it, and then it's fine. So when you exit out of the process, it gets cleaned up. If that were production code or something, that wouldn't fly. And then the other thing would be you can have a pointer to a piece of memory that you free, and you can then actually re-access that pointer. And then you're just reading kind of random bits from the heap. And you could be like overwriting stuff. You could be corrupting your memory. Mm-hmm. So I had like this one really gnarly error, and it was like 6 hours of segmentation fault. Mm-hmm. I've really been appreciative of the Rust compiler being very, very, very helpful with their error messages. And even providing those little like, and if you want more information, here's like the little code you can check out. And then it links to like the docs and stuff. Like that's amazing. You do not have that kind of stuff in C.
Very helpful, for sure.
So if C is so bad, what does Rust do to make it a little bit easier for us?
So Rust does not do garbage collecting like some other high-level languages would do, like JavaScript. So it's like Rust kind of gives you the best of both worlds in some ways. So Rust's memory is managed through this system called ownership, and it basically defines a set of rules that the compiler checks at compile time, I guess. And so in Rust, each value has a variable that's called its owner, and you can only have one owner at a time. And the owner of the data, when it goes out of scope, then Rust will automatically call this drop function, and that will go ahead and free up that memory for you. So it's pretty neat because it's kind of giving you the benefits of the stack in regards to scope. So when a frame is popped off the stack, which a frame would represent a scope, a block of code, when that's popped off, then any things that are pointing to the heap get cleaned up for you. So it's a pretty cool idea.
It's amazing. Why didn't they think about that
Yeah,
25 years ago or something?
I know.
I don't know.
It's awesome.
So can I make sure I understand? Ask you a couple of questions, I guess.
Sure, I'll do my best.
So what you're saying is like we add a frame, like this frame here.
Yep.
And if I had some sort of dynamic variable, like a string or something.
So if you added string third there, that was capital S string, not a pointer.
Yes. Right. So if I add a real string, you're saying it'll actually allocate something on the heap for me, and that when this frame gets popped, it'll actually do cleanup for me also?
Yes. I guess I'm not totally clear on the allocating part. I guess when you declare the variable, that's when it allocates. It does that under the hood, but I can't remember if there was like a function that it calls like drop.
Yeah. So probably when it's like that, I think we saw like that string : from
Right.
syntax. So you're saying that's probably allocating the heap space?
Yeah.
Okay.
What I'm saying, I guess, is I don't know exactly what's going on under the hood there, whatever, but I guess for our purposes, it's allocating some memory.
Okay, cool. So I guess one thing that I kind of start to wonder then is in C, like often you'll have like a pointer, and then sometimes you'll have maybe like even a pointer that points to a pointer, or you'll have like kind of more advanced patterns where it's like you have to have multiple things being able to read something. And one of the things that really jumped out to me in the chapter was this idea of a reference. To me, a reference kind of seemed like a pointer with superpowers a little bit. The big contrast is like a reference isn't an owner. It's just a borrower.
So are references pointers then? Or are they do more than that?
I don't think the chapter went into it too much, but I was looking at the API docs, and I think a reference has like 3 parts. It's got inside of it, it's got like a pointer. So that's like this piece. That's like 1/3 of it. And then it also has basically this data of the length, and then it's got like a capacity. So you could maybe like allocate a bunch of memory at the beginning, and you don't have to fill it all up. I guess if you get over it, it automatically increases the size on the heap.
Okay. So how does that relate to a C pointer? I just kind of assumed that's what it was like in C as well.
So with C, you just have the address.
Okay, it's just an address. Gotcha.
It's just the address. And so like this is actually an array example in C. And so like this is an array of 4 integers. And to be able to know that, you have to have like a separate variable here, like this thing. And then basically like the compiler just knows an integer is a certain size. We have 4 of these things. And so it basically calculates the offset based on the value. It works. It's just kind of kludgy. And then you have to like keep track of this count thing, which is a big pain. If you like add an additional value to the array, like you have to remember to update this kind of. And so it's just a whole nother kind of thing you have to juggle to keep everything in sync. So it seems like the superpower of like a reference then is all of that kind of state is handled by like the data type. Seems quite a bit easier, but passing a reference looks very similar to passing a pointer in C. Yeah, so I know like the one other thing that kind of got mentioned in the chapter was this idea of slices.
Yeah, so slices are pretty cool. I kind of thought of it as like a way to kind of peek into an array. If maybe you
Hmm.
don't want to see the whole thing, you get a little window into it. So slices are a data type. They don't have the concept of ownership because it's not a slice isn't created directly. It's like derived from an existing variable, and they let you refer to some subsequence of an array. So you can basically specify a range, like I want index 1 through 5 of this array, and it lets you reference that. So you can take a slice of an array, which means you can also take a slice of a vector, which I guess we don't really know what it is yet, but you can do that.
Have you been reading ahead, Kate?
I just a little bit,
Oh no, you're
but
busted. Okay.
so you can also take a slice of a capital S string type or a string literal, because those things behind the scenes are just arrays. Like if we use that example you have up there where you have an array of ages, those things, like if that were a string literal that maybe said Sean or Kate, each memory address there points to a character. You could take a slice of this string literal by maybe pointing to the first index and the last index, and then it would return 8.
So what would the range be for that?
1, and then you could either do like, oh, I think it's +1, right? So like it would be 1 to 4, maybe?
Let me think. Yeah, so the last one is excluded. So yeah, I think that's right. And then you're saying there's an even fancier way to do it then?
Yeah, so Rust also, if you're just want to go to the end of the collection, you could just leave out the last index. It's like a shorthand. You can just go to the end, or you could leave out the first index and just start at the beginning. So
Um,
basically, this is a way to access some part of an array without having to copy the whole thing.
let me make sure I got it. So we have this data on the heap, and if you have a slice, and you say like 1 4, so we have AIT. Does that actually allocate any additional memory on the heap here, or do we just basically reuse what we already had?
We reuse what we already have.
Ah, okay, cool. That sounds pretty efficient.
Yep. Which
Okay.
is why it doesn't have the concept of ownership, really,
Hmm.
because we're pointing to something that already has an owner,
Okay, cool.
and there can't be more
So
than
it's
one owner.
so it's like a special form of borrowing, kind of. Then,
Yeah.
shall we go to the code then?
Yeah, let's do it.
Okay. All right. So these are just a bunch of different examples that I basically developed off the chapter. Okay, so I've unselected the first example here, and let's make sure everyone can see that. For audience awareness, I'm passing this special flag to present the warnings from being presented, and that's just because I have some different utility functions down here, which I'm not using. And the compiler is very helpful, and it throws a bunch of warnings about that, but like, we know that. That's fine. That's fine for our purposes here.
Yeah, it's all good, compiler.
It's all good. Okay, so I guess I'll take this first code example here. So we talked about the stack, and there are a bunch of different values that basically exist on the call stack. Things like integers, floats, characters, string literals, booleans, and tuples that contain only things that can live on the stack. And so here is an example of a string literal. And so this is not allocated on the heap, it's on the stack, as I understand it. And so it behaves a little bit differently than a full-blown string, which is allocated on the heap. We can go ahead and just create our string literal. We can define a second variable here and set it equal to a string literal. And this is actually basically copying the value. So the value exists twice in the stack. And that allows us to just print it twice. So you can see that right here.
Yep. So why would a string literal not be mutable?
Why would a string literal not be mutable? So it's since it's on the call stack, I guess this might be getting a little bit deeper into compiler theory, but like as I understand it, the compiler takes our source code here, and this value basically is used to define the call stack when it's first created. And since we're in the main function, I guess that's probably some special area, the binary or something. But when the main call stack is created, it knows that we have two different values, each with the same length, I presume. So I don't know, 2 strings of 5 characters or whatever.
Yep.
I don't know. I've never taken a compiler class. That's interesting.
I think you
to
were
think about, though.
you were going a little deeper than I was thinking.
One of the things the chapter did mention is it mentioned this copy trait.
Yeah.
And so everything with the copy trait, whenever you kind of reassign it like this, it copies the value. And everything that has that copy trait, I guess, lives on the stack.
And the other thing about copying is that it's for these specific types too, because there isn't really a big like performance hit if you copy these kind of values, from what I understand. Like it's not that big of a deal to copy hello over into another memory space, whereas it might be if you have like a dynamic kind of variable that uses the heap.
Yeah, because I think the compiler basically kind of figures out your logic, and so it's like kind of computed at compile time.
Right.
So there isn't really an overhead, I guess, when you execute the binary.
Yeah. Cool. So this next example, we are defining a string literal, and then we're also defining a mutable variable that holds a capital S string value, and it's allocating space for it on the heap. And we are now pushing a little part of a string onto that greeting on the heap variable. And we should see hello Kait.
Ah, it works.
And that's because the capital S strings are on the heap.
So that kind of sounds like I could basically duplicate this line and then add like some celebratory emojis or something if I wanted.
I think you could.
Let's try it. Okay. So in Windows 10, I have this awesome emoji picker.
Wow.
I hit Windows key period, and then I get this thing.
Nice.
Let's do raised hands. Boom. Let's see what happens. Ah!
Nice.
Cool. So mutable stuff is fun.
It is. It's almost like you could do that forever.
Yeah. I've got a lot of RAM. I think we could.
Pretty much. I don't know, how many emojis would it take to run out of space?
Yeah, it's tough because some of them take up longer. Like I know, like some of the ones that are like all the family members, they're each individual Unicodes in a sequence,
really?
basically.
That makes sense, I guess.
Yeah, and that's why some of the like the Rockstar one with the male and female rock stars, like if you don't fully support that, it's like a generic rock star and then either the male or female symbol right after.
Yeah.
I don't know if have you ever seen that?
I have, yes.
Yeah. This is basically an extension of the previous example where we start with a string literal, then we convert it to a capital S string, I guess what we're calling it.
Is there a better
Like,
way to say that?
so, well, I guess Java has this term like boxing and unboxing,
Okay.
where it's like if you take the primitive and then you turn it into the full-blown thing with all the methods and whatnot, you're like boxing, I think,
Ah.
and unboxing.
I would
Yeah.
think the opposite. Like unboxing would be getting all of the
There's a
methods
40% chance I'm saying it backwards, so
Okay.
it could be.
Gotcha.
But yeah, it's I don't know if there's a better term. In JavaScript, it's kind of like how you have those weird DOM things that are like not full blown.
Oh yeah, yeah.
It's not an array; it's an array-like thing, and
Yep.
so then you have to cast it into a real array.
Exactly.
So we've got the primitive string literal, and then we are casting or boxing or unboxing, whatever the heck, into the capital S string here, which lives on the heap. And one of the nifty things about Rust ownership here is that we have this statement, and it actually behaves quite a bit differently, like from this. So these two lines, line 6 and line 21, look similar. But if you can remember on line 6 when we did this, it copied because everything was in the stack. But since this is on the heap, it just basically does a move. And so the owning variable becomes this greeting on the heap 2, which is kind of like, I kind of think of it like a shallow copy, like the memory address and kind of the meta information about the capacity and length moves over to the other owning variable.
Right.
And then this original owning variable is like invalidated. So I don't have it uncommented because we get an error, but if I were to uncomment this line here, we would see an angry message from the compiler that says basically, hey, you're borrowing a value after you've moved it, and which is like, it's invalid, it's inaccessible. But after we move it, we can then access the data on the thing we moved it to. So if I run this here, there we go, we get hello.
Cool. So then on lines 25 through 27, here's, I guess, a way to copy a variable over while maybe keeping that original variable, keeping it active, I guess, and not throwing it away, right? So if on line 25, we're doing a deep clone of greeting on the heap 2. And that is actually taking the data at a certain memory address and making a whole new entry for it, and then storing the pointer to that new entry in greeting on the heap 3. Yeah. So the question is, what happens to that original variable that we've cloned? I think that it's still there because we are deep cloning it. The ownership, it's now two different memory addresses. So I am guessing that the first one is still there, I guess. It hasn't been discarded yet or invalidated.
All right, let's run in a second. But I guess, so you're saying it's going to be like this first example then, where we were kind of just copying on the stack, and then by calling a clone, we have a similar copy behavior on the heap? Maybe.
I'm not 100%, but that I would say I'm 80%.
All right, I'm gonna run it. Let's see. Okay, it looks like both of them had hello, so it looks like they copied.
But they're different hellos.
They're different hellos. Yeah, so I don't know how to do it, but there's some way to actually see the memory address of what the reference is pointing to.
Oh, yeah?
But
that'd be cool.
We'll have to, yeah, I didn't do enough homework to know how to do that, Kate, sorry. But I think you're right. I think these are different things. So to kind of continue the discussion of borrowing and moving a variable, so like transferring ownership from one variable to another. This example here is basically doing a move, but it's moving into the scope of the function. So like these lines are in kind of the main frame on the call stack. Main frame.
Sorry.
and then we call this function here giveth and taketh away, and we're passing it in as a argument here. And then so if we go down here, like we've got a whole nother block scope here, and so we're passing ownership into, I think, this variable, and then at like once we do this variable inside of this block scope owns that bit of the heap, and so it runs to completion, just prints out, hits the end of the block, and then because this owning variable some string isn't passed back or anything, it calls drop, and then I think the data gets dropped from the heap. So that's why it gets taketh awayeth. So if I were to run this line here, I think we would get another error similar to above. But let's see what happens. Fame has been taketh away. If I do that, now I get an angry squiggly. Value borrowed here after move. And then we see like kind of the life cycle of, I guess, the heap value there.
I'm trying to visualize it with this kind of our mental model of a stack. Like it's in this main stack frame, and then it kind of gets pushed up to the one above it almost.
Yeah, so it seems like if we were to look at this kind of example, we have like we have some sort of variable here in main. And then we pass it in as an argument into this other function. And so then ownership gets transferred up here and then like gets invalidated down here.
What does that do to actually like where the memory is located? Like what does the value actually stay in the same place? Because I know we said it's like a move operation. Do you think the data moves?
So I think the heap, like the heap address, stays the same. The only thing that moves is it's like reassigning the owner, I guess. And I mean, to a certain degree, it's like it really is moving to us because we're like moving to a different frame with a different scope.
Right, but the data itself isn't moving. It's moved owners.
Right, the heap stuff is like, I'm the same as I've always been.
I just got a new...
at the same place.
I have a new dad.
Yeah, exactly.
So things can be reassigned to the same variable or shadowed. Okay, so here you are declaring thing2 as a capital S string on the heap, and then you are shadowing that variable with another thing2 declaration and passing the first variable into this giveth and returneth function. So the ownership is going from the first thing2 into the giveth and returneth function. So maybe we could
want to look at that?
Take a look at that. Let's
see, can I open? Oh,
there you go. Giveth and returneth on line 70 there. So it is returning the value now on line 72. So I believe that ownership is now transferred back to the thing2 on line 38. So returning actually is a way of transferring ownership. And if we run line 39, I believe that we should see self-respect.
Which is important. Everyone should have ample amounts of that.
It is, yes, should be returned.
So you're saying we declare on the heap, it's in thing2, and then we pass it into here, which transfers ownership to some string.
So it goes to a different frame.
into this new frame gets pushed to the top of the call stack, and this runs.
And an important part about that too is that when this new frame is pushed, the main frame is it pauses, so it's going to stop executing until it gets a return value from giveth and returneth, or it doesn't. But in this case, we do.
So so the sum string gets returned here then, and so you're saying that it's like they almost have like a dance off or something, and it's like this frame is dancing, and then this frame dances, and then this frame dances again or something.
Sure, why not?
Okay, let's see.
Nice.
Cool. Okay. So I came up with a couple of examples of where I'm lending you stuff. And so like do you even know what a DVD is, Kait? Have you owned a DVD before?
I did, yes. We had a whole bookshelf of DVDs.
Okay. What about a laser disc?
No.
A laser disc is like a similar technology to DVDs, but like the technology was less advanced, and so they're like the size of a vinyl record. And you put these huge video discs, and it's like made like a CD, but it's the size of a vinyl record, and you put it into this big video player, and then I think you got like 65 or 70 minutes of video, and so like no movie could fit on the whole thing. You would actually have to take it out, flip it over, and then on the B side, then you get the second half of the movie.
Wow. What era was this? I missed that.
So that was probably like early 90s cutting edge technology kind of thing.
Interesting. Yeah.
But I never had a video disc. You had to be like pretty fancy and rich to have those. But I did have DVDs, and I have DVDs. And I think one of my favorite DVDs is this movie called Idiocracy. I don't know. Have you seen that one?
No, I think you're gonna have to lend it to me.
Oh, I'm gonna have to lend it to you. Okay, so it's an excellent movie, and I recommend it to the entire audience. Check it out. It's I think Mike Judge is the director, and so here I'm basically declaring a string on the heap with the name of my favorite DVD, and then I am passing a immutable reference to that string on the heap to this function here. So since I'm passing a reference, ownership isn't changing, but then within the context of this block scope here, you have the ability to read the data from the heap. So Kait borrows Idiocracy, then the scope ends. And since I never transferred ownership, there wasn't anything dropped, and I have access to the same data on the heap after that. Or so, yeah. So I think let's see what happens. There you go.
Great.
So you watch it, and then I watch it again because it's a great movie.
So you're just telling that function, hey, here's the memory address of favorite DVD, and you can do what you want with it. But
yeah. So I think it's like, it's not just the memory address, it's also that capacity and the thing.
I should say reference.
So it's got the whole reference, but it's not the owner, so it doesn't trigger anything getting dropped. And both, I guess, like a thing and favorite DVD both point to the same address on the heap, I believe. And since these are immutable references, I know the book mentioned one of the neat things with immutable references is you can have as many of them as you want, basically. So like, I guess you can't do it in reality because like I only have the one DVD, but if it was like a digital copy and I was a internet pirate, I could like, I don't know, lend out shady illegal digital copies and then get sued for it, I guess.
Yep. Not a great plan, but
Not a great plan.
okay, so mutable borrowing via references. So basically, this is the same example that we just talked about, except now I am able to mutate the variable that I'm receiving from the main frame. This is nice because, like, as the owner of that cups of sugar variable, you can say specifically, like, I'm going to let you mutate this. So it gives you some power there to make sure like things aren't changing if you don't want them to. And then so it looks like in the borrows with mutation function, I am using all of the sugar and returning on line 83 the string 0. And so on line 51, when we print this out, I expect that I give you an empty cup back.
It's kind of rude.
It is very rude of me.
Yeah. So you borrow 6 cups of sugar, you use them all, you return an empty cup, and I got to go to the store. Okay.
I mean, really, I should go to the store, but yeah.
What are friends for? It's okay.
All right.
So,
I appreciate it.
So like up here, I mentioned that you can have like as many immutable copies or immutable references to a value on the heap as you want. How does that work with like having a mutable reference?
I would assume that you can't because that I feel like might have some race conditions. Like if two things are trying to mutate the reference at the same time, or one thing mutates it and then another function is expecting something different. I don't know. Yeah, I'm guessing no.
Yeah. So, well, I guess we'll investigate that later. I think there's a fearless concurrency chapter in the future.
Cool.
But I think I was trying that earlier and I was getting some compiler errors basically saying like you already borrowed this as a mutable thing, so you can't do it again. So it seems like you can only do it once, I guess.
Right, that makes sense.
So this basically slices. I'm creating a string, capital S string on the heap with my name. And then I am pre-allocating a capital S string on the heap that's actually empty. It's just got like a buffer of 20 characters pre-allocated.
Mm-hmm.
But it's like once I have that, then I can use slices to get my last name.
Mm-hmm.
So that's 5 to the M. That's McBride. Then I add a comma space, and then I get my first name. And so then when I print that back out, it's just like reverses first name to last name, comma, first name, hopefully.
Mm-hmm.
Okay.
Nice. So this name reversed variable, that's kind of a way to have like an empty string to play around with.
Yeah. And I feel like I probably didn't have to do this. Like if I were to just do like with capacity 0, I think it resizes. Let's see. Yeah.
So could you just do string, or do you have to like, or like new string?
Yeah, how's that work? New string.
I don't remember exactly the syntax.
No, I'm typing in like Java.
Yeah.
How about that?
Yeah. That's what I was thinking.
So that's an even better way. Learning
Sweet.
stuff as we go here on the fly.
Awesome.
Yeah, so I think that's pretty much everything that we kind of covered in the chapter. So if we were to like, I guess, change this to use your name, like what would we have to kind of change here? What do you think?
So
did I spell Caitlin right or not?
you did. Great job.
Okay, good.
So I think that would be instead of 5 on line 60, you would take a slice from 7. Instead of 4, you would do 6 or 5. I think 5.
You want me to try it?
Sure. Oh, okay. Oh, I think I mixed these up. So the line 62 would be 7.
Line 62 would be 7.
Yep. And then line 60 would be 8. Yes.
Okay, cool.
Sorry, I'm like counting characters.
Math is hard.
It is.
All
right, but this was great because I feel it just feels like all languages should do it this way. It just makes so much sense. It's more speaking about ownership and how it handles this.
Oh yeah, yeah. So it's cool because it feels like you almost have garbage collection, but you don't have the overhead of running that.
Right.
So I know like it's kind of getting to be a big deal with WebAssembly. A lot of languages like Go want to compile to WebAssembly, but since the WebAssembly runtime doesn't provide a garbage collection algorithm out of the box, basically they have to compile that and ship that, which is kind of a pain. And so I think like this kind of ownership thing is like why Rust in particular is really popular for WebAssembly right now. It's not too bad. I do think it's a lot easier than C, and so it's like I hope I can, if I take a class and I have to do systems programming, I hope I can convince the professor to use Rust instead of C, so I can have a little bit of an easier time. But
yeah,
I don't know. Some of them are kind of like backwards a little bit.
Yeah. Old school.
Oh, cool. Well, thank you for going through this chapter with me. So what do we have coming up next? Do you know?
I do. The next chapter is structs.
Okay, cool.
Using structs to structure related data. Sounds like a good time.
Yeah. Yeah, so we've used tuples, which is like kind of a way to structure a little bit, but we'll be learning all sorts of new techniques. It'll be great.
Yeah. All right. Bye, everyone.
Bye, everyone.